Hello everyone. Today I would like to demonstrate a pricing engine for commercial airlines. So here is the problem statement. So airlines face a critical challenge of optimizing the price to maximize the revenue and to ensure the flying at a near capacity level. So this project will address the need for a data-driven and automated pricing engine that dynamically adjusts the ticket price based on the predicted demand, conversion rates, and the remaining capacity to achieve the optimal revenue and capacity utilization. So here are some challenges for airlines. So first one is the revenue optimization. So airline can sell the tickets at a low price to ensure full capacity, but this will leave a lot of money on the table. So if they sell the price too high, then no one will going to buy it. And also, they face capacity utilization problem. So they want to achieve the optimal utilization, but at the same time, they will need to make sure um, the revenue is at the target level. They also need to ensure the price is competitive because there are a lot of competitors in the market. And at last, there will be customer behavior that need to be taken into consideration. And here are some pain points for airlines. So first, the manual pricing is inefficient. A lot of the airlines are using manual pricing. This takes a lot of manpower, and it takes a lot of time to collect all the data needed to price each market. And this is also a very repetitive work because you need to repeat all your action for all the departure and arrival cities. So there's a big opportunity for machine learning model to kick in and make big improvement on automation. And the pricing engine is also very data incentive because the demand is changing, so you need to monitor the market at real time and update your demand model. And also there will be supply and demand mismatch because the supply is also changing dramatically every day. So you need to rebalance the supply and demand um, at a higher frequency. A lot of airline has static pricing structure, so they have fixed price points, and those price points are really difficult to change, and it's usually not optimal for each different market situations. So in all, there's like a missed revenue opportunity for all the airlines. So there's like a big incentive for airlines to implement real-time and automated pricing engine. So here is what we mean by pricing engine. So when there is a travel search, so the search will reach to the pricing engine, and the pricing engine will return the price and itinerary to the customer. So let's have a closer look on how the pricing engine works. So in the pricing engine in my demo, there are two major models. The first part is the search forecast, and the second part is the conversion model. So we need to have a model to forecast the demand. So the demand is basically the number of searches for that flight and multiplied by the conversion rate. So the conversion rate is basically the booking divided by the number of searches. So if we can implement machine learning models for those two prediction, we can have our demand prediction to match the supply. So we use a simple machine learning model called gradient boosting for the demonstration. In the real project, you can use more complicated models like um, neural networks if necessary. So here we list all the factors that we have in this model. So for the search forecast, we have the departure and arrival airport. We have the call-out days. The call-out days is basically the days between departure and booking. And we also consider day of week and also seasonality. In the conversion model, we have call-out days, the price that returned to the customer, seasonality, and departure and arrival airports. So here I want to also introduce some basic terminologies for airlines. So one terminology we already mentioned is the call-out days, which is the days between departure and the booking. And another terminology we want to consider here is called the booking curve. Basically, booking curve is the cumulative bookings for each flight on certain departure days. So the x-axis is the call-out date, and the y-axis is the cumulative booking number. So this is usually an increasing curve that, for example, that start at callout 90 means 90 days out before departure, and the booking will accumulate across the callout days. So at a callout 0, which is also the departure date, we would like to have the booking number equal to the capacity. And finally, we have the optimization part. So with all the components we have now, the search forecast and the commercial model, we can come to our optimization. The optimization is basically solve the equation with cumulative booking equal to our capacity at the time of departure. So each airline will not reach 100 capacity because there are certain situations that we need to take into consideration, and they usually multiply the capacity by a load factor. So load factor is the percentage that the airplane is full. So low-cost carriers usually target a higher load factor, like range from 85 to 90%. In our case study, we just assume the load factor equal to 1. That will simplify our demo. So with the basically structure of our pricing engine, we can go to an example here. So in this notebook, we are taking an example of the flight from Atlanta to Las Vegas. And the departure date we are considering here is December 1st, 2025. So we are using all the 2024 data. So all the data we are using here are synthetic generated data, just for the demonstration purpose. So we have a 1-year data for this market, and we have the search data, like a historical search data, and also historical booking data for the year 2024. So here is how we generate those like a synthetic data, and we can take a look here how the historical data look like. So on the top left um, graph, we have the search along the callout days. So we start at callout day 90, and the search volume will increase at certain days, and then as they approach the departure date, the search volume will drop. And this graph shows the average ticket price by callout days. So the pattern here is that the ticket price will quite stable at a lower level, but increase as the days approaching the departure date. And on the bottom section, we have how the conversion rate changes along the callout days, and also the correlation between searches and the ticket price. Now we're using the generated synthetic data to train our models. So first we train the search forecast model. So we use the gradient boosting model and using the 2024 data for the training. So here are some metric we have. So we have R square, MSE. So the metric doesn't really matter because the data is not real. And here we can have a visualization of the model. So the actual searches versus predicted searches. So this shows how our prediction look like against the actual search. And here is the feature importance plot for this model. The second model we are training is a conversion rate model. So similarly, we are using the gradient boosting regressor model, and we have all the metric for the model here. And here's the visualization of how the predicted conversion rate look like against the actual conversion rate. And we also have the feature importance for this model. So now we came to the optimization part. So we want to optimize the price for each callout days so that the cumulative booking will be equal to capacity at the day of departure. So we have the predicted demand, which is basically the number of searches multiplied by the conversion rate. We have all the functions already developed above. So for each callout date and also for each price point, we have the conversion rate, and we also have the search forecast. So we can multiply them together and do a summation along the callout days and set that equal to the capacity of the aircraft. And by solving the equation, we will get the optimal price for each callout days. So this is what we have, the optimal price, and we can also have a visualization of our pricing strategy. So this shows the result of our pricing engine. So basically along the callout 80 to callout 0, we have our optimal price here. So the optimal price will set a higher level but decrease along the callout days, but at certain callout days it will increase and stay almost the same when it approaches the departure date. We have the demand and supply here, and also we have the daily booking, which is the um, search multiplied by the conversion rate. And we can also plot the optimal price versus the demand here. And here is basically an overview of all the search and conversion rate along the call-out rate. So here the search volume, here's the conversion rate, and we can multiply them together with the ticket price to get the expected daily revenue by the call-out days. So now we have the output from the pricing engine, and we can output that to a CSV file or to a database. So this pricing engine, we can run this pricing engine at real time, and it will change depending on different market conditions, and also depends on the capacity. If there's some change on the capacity, so the pricing engine will recalculate everything and generate the new price. So this gives us a real-time and also optimized pricing for this market.